Thanks, Andrea. Thank you, Michael, Martin, and Suzanne, for organizing this wonderful workshop. I've been learning a lot throughout the last 2 days. So, yeah, my talk today is going to be about sort of videography of magnetic domain walls in a cuprate mod insulator. It's a neat experiment, I think, I wanted to share a little bit with you about. It's new, unpublished work, so comments are very welcome. So before I start, maybe I'll just sort of set the stage for why we stumbled upon this problem. You know, generally, we're very interested in light-induced ultrafast dynamics of mod antiferromagnets, and there's a lot of activity in the field surrounding this topic. In a very sort of simplistic way, you can think about all the different ways you can manipulate this phase, you know, through pumping at different photon energies. So for instance, if this is some sort of prototypical conductivity curve for, you know, a 2D mod antiferromagnet, and you can think about ways of pumping at very low energies where you're on resonance with single phonon or magnon excitations, and we've heard some really nice work this morning already on how, you know, nonlinear phononics can be leveraged to, you know, realize different perhaps magnetic phases or other interesting phenomena. You can pump on magnons to, for example, look at magnon nonlinearities. You can then progress up a little bit higher and pump photon energy and think about being on resonance with multi-magnon or multi-phonon modes. This is a regime where you can think about experiments on parametric amplification or on impulsive stimulated Raman scattering, for example, and there's, you know, a whole body of literature. I'm unfairly singling out a few just as an example, but you know, the activity is very, very broad. A little bit, you know, higher up in energy scale, where you're sort of off resonance from collective modes, but far away from other transitions. You can sort of label this as the transparency window, where there's been a lot of nice work on phenomena like Keldysh crossovers, Floquet engineering. You know, this is a good regime in which you might be able to realize some of the ideas, for example, that Martin and coworkers have worked on in the context of renormalizing magnetic exchange interactions to realize different magnetic states of matter while minimizing the effects of heating. There's been some very nice solid-state high harmonic generation work that's been also carried out in this regime. Further up, you start encountering DD resonances, and there's been, again, a big body of work looking, for example, at how, you know, resonantly exciting DD transitions can maybe modify exchange, you know, magnetic anisotropies in systems as a means of, again, exciting collective modes or designing new magnetic phases. And then at higher energies near the band edge, you can do things where you excite exciton resonances, for example, and affect other collective degrees of freedom this way. And then as you get to very high photon energies, you know, above the band edge, this is the regime of interband resonances, and there's a lot of rich work on photodoping mod antiferromagnets, ideas related to quench dynamics, either magnetic or insulator to metal transitions, and their sort of results in metastable states have all been discussed in the context of driving in this regime. I think is there a hand up there? Yeah. Needless to say, please interrupt throughout.
So maybe I missed this, but I would have imagined optically one creates pairs of magnons. Then shouldn't we have a broadened kind of set of peaks on the left? Like are these like single magnon peaks?
These are single magnon peaks. Yeah.
So are these systems with spin orbit coupling?
I'm sorry?
Are you considering system with spin orbit coupling?
To be able to, or you can do it directly through the magnetic field of light.
Okay.
They're both possible.
Okay, thank you.
Yeah, thanks. Okay, so my group has also been interested in this sort of playground. And I just wanted to sort of give you a snapshot of some of the works that we've been involved in, maybe to seed some conversations later at dinner. So we've been thinking about problems like photodoping-induced demagnetization in mod antiferromagnets. We've been working with some members in this audience on parametric magnon pumping. We've been looking a lot at Hubbard excitons, again with people in this audience, Keltish crossover dynamics, metastable magnetic states in mod antiferromagnets, flow K engineering, and so on. I say this to set the stage for what I'm actually going to talk about, which is the following. In all of these experiments, we often, or always, look at spatially averaged dynamics. Spatially averaged over the size of your probe beam. Some members of my group, one day, began to sort of become curious about questions related to dynamics of inhomogeneities at the mesoscale. What happens to those things when you start pumping the systems in the various ways that I talked about? So that's the subject of my talk, and this is really the brainchild of my former postdoc, Kyle Seiler, who just started a faculty position at the University of Arizona. While he was at Caltech, he worked with my graduate student, Dan Van Beveren, and we've really benefited from theory collaborations with Ran Sheng and his student Han-Tao Zhang at UC Riverside. They've done some beautiful numerical simulations that are consistent with our data. I won't have time to present those today, but I'm happy to discuss those afterwards. And our crystals of cuprates come from Young Li's group and his former postdoc, Costel Rotundu. Okay, and thank you to the funding agencies. Okay, so before I tell you about the material, let me just sort of embed the talk in a little bit of context of magnetic domain wall technologies. So there's a lot of reasons to be interested in magnetic domain wall dynamics, both from a fundamental and applications perspective. On the application side, there are really interesting ideas like, Stuart Parkin's racetrack memory idea, where you sort of you encode, ones and zeros in different magnetic domains that you then, push down sort of 1D wires. And on the fundamental physics side, there's also been a lot of activity attempting to understand different mechanisms by which you could drive magnetic domain walls. And this is sort of a sampling of some of the major mechanisms that have been investigated, including applying a magnetic field, applying temperature gradients, sort of driving spin polarized charge currents, and inducing domain wall motion through spin transfer torques, or using pure spin currents or Curie magnons to drive magnetic domain walls through mechanisms like spin orbit torques, for example. And especially in recent years, there's been growing interest in looking at magnetic domain wall dynamics in antiferromagnets, because there's an advantage as far as speed and also robustness against environmental noise that's been conjectured for AFM systems. Okay? So the talk today is going to be focused on antiferromagnetic mod insulators that may have some applications to this field. So in particular, today I'm going to talk about light-driven antiferromagnetic domain wall dynamics. And in this particular compound, I'm going to show that the propagation speed can be very fast, actually faster than the speed of sound in this particular material. And so the talk will actually follow this logic. I'm just going to talk about all the challenges associated with these experiments, and then sort of tell you about how we've resolved them one by one. The first one is sensitivity. So, if you go into the literature, you'll see the common statement that antiferromagnets are sort of difficult to optically resolve because they don't have a net moment. So, how do we overcome that? Well, we chose to look at cuprates, actually for other reasons to begin with, but it turns out that there's a particular cuprate family that's very good for this project. But let me start with sort of the standard cuprate square lattice, right? So you've got a square lattice of copper moments that order in this sort of bipartite way below a critical temperature. And interactions are mediated by oxygen atoms that sit between neighboring copper sites, okay? And then you can sort of define a antiferromagnetic order parameter L, in this case, pointing vertically, okay? So this has no net magnetic moment. Okay, so it's challenging to resolve optically. However, there's a particular variant of cuprates, namely these oxychlorides. Okay, and this particular compound has this 2,3,4,2 stoichiometry, so sometimes I'll refer to these as 2,3,4,2s. And the special thing about these is that it possesses the regular cuprate square lattice. However, it has an additional, what we call a copper 2 sublattice, which is in the same plane as the original copper 1s. Okay, these are all coplanar, but they sit in every other center of, they sit in the center of every other square plaquette on the lattice. Okay? So the exchange interactions between the copper 1 sublattice, okay, are very strong. You know, they're in typical cuprates, they're on the order of 100 MeV. And so the copper 1 sublattice orders at very high temperatures, in this case about 380 Kelvin. Okay? But the coupling to copper 2s are weak. The coupling between copper 2s are also weak. And so the copper 2 sublattice stays paramagnetic down to very, very low temperatures, which we won't talk about today. Okay? So for the purpose of the talk, imagine the copper 2s as still being paramagnetic. However, there's a very weak dipolar coupling between the copper 1 sublattice and the copper 2 sublattice.
So these are both D9.
Yes, that's right. So if you sort of draw the magnetic field around each spin, you can sort of convince yourself that there's a net field at the center at the positions of these copper 2s that all point in the same direction, and that weak dipolar coupling is what polarizes this paramagnetic copper 2 sublattice that creates a net magnetization this way. Okay? It's a very weak magnetization on the order of 10 to the minus 3 Bohr magnetons per unit cell. But nonetheless, second harmonic generation turns out to be very good at detecting small in-plane moments. And so it's these sort of reporter copper 2 ions that we're going to use to make statements about the the orientation of antiferromagnetism in this compound. Okay. Okay. If I don't see you, just shout out. Okay. So Anshul already gave a great introduction to second harmonic generation. I won't say too much more, other than the experiments we do are all going to be second harmonic generation today, but it's going to be a combination of polarimetry and imaging. And on the polarimetry side, what we do is we have an oblique incidence geometry, omega in, 2 omega out. And in our experiments, we have the ability to apply an in-plane magnetic field, H, which we can rotate in the plane. And moreover, we have the ability to rotate the scattering plane. So in these polarimetry plots I'll show you in a second, what we're showing is the amplitude of the second harmonic intensity as a function of the scattering plane angle, phi. Okay, so 2342 is a bulk centrosymmetric crystal. And as you've already heard, the bulk electric dipole contribution SHG is forbidden by symmetry in these materials, but nonetheless, you can get higher multipole contributions. And in particular, I'll be talking about two, magnetic dipole and electric quadrupole, both of bulk origin, okay? Those are going to be the two dominant radiation channels. Okay, so going back to sensitivity. So how do we leverage these copper 2 sublattice ions as a means to detect AFM order in 2342? So on the right is a zero magnetic field SHG polarimetry plot taken on a single domain in this material. It's paramagnetic, so there's no broken rotational symmetry because there's no net magnetization. And you can see that the pattern respects the tetragonal symmetry of the lattice. It's got fourfold rotational symmetry. And you can fit these patterns to different processes refined under different symmetry groups. And in this particular case, it fits this electric quadrupole bulk SHG refined within this 4/MMM centrosymmetric tetragonal crystallographic point group. Okay, and this term is pretty temperature independent. When you cool it down at low temperatures below TNAL, this pattern develops this one very big lobe. Okay, and if you track the intensity of that big lobe, it follows this sort of order parameter like line shape. In fact, you can analyze sort of the functional form of this and extract a critical exponent that matches well with what people see in neutron scattering. So we think there's a linear coupling between the susceptibility that's sensitive to magnetism and the magnetic order parameter in the system. Okay, so at least from a symmetry point of view, you can see that the development of this net magnetization, because of the copper-2 sublattice, gives rise to the symmetry breaking. So qualitatively, this is how you can track the orientation of your magnetic domain. Sort of in more detail, this kind of pattern arises from a coherent superposition between this, fourfold symmetric crystallographic contribution I just mentioned, as well as a magnetic dipole contribution. Okay, it's a P equals chi EH type process, a little bit different from the one Anshul talked about, refined under this M prime magnetic point group. Okay, so M prime just means the combination of mirror and time reversal is a symmetry. Okay, so just to orient you one more time, the orientation of this big lobe is along a direction parallel to the antiferromagnetic order parameter and perpendicular to the net magnetization. Okay. Okay. So equipped with this technique, you can then go in spot by spot on the material and determine, if the net M magnetization is pointing in one of 4 directions, thereby also resolving the copper-1 sublattice orientation. Yep, a question in the back.
Why are you mentioning the magnetization when the plot on the left, I think, was still at much higher temperature than the ordering of the copper 2s?
Oh, okay, yeah. So the question, okay, yeah. So let me be super clear again. The copper 1s order at 380 Kelvin. Above 380, the whole thing's paramagnetic. But below TN1, only the copper 1s order. The copper 2s are still a paramagnetic sublattice, but the dipolar coupling between copper 1 and copper 2 polarizes that paramagnetic sublattice. Yeah, and it's not until much lower temperatures do the copper 2s then also antiferromagnetically order. Is that okay? Yeah, there's a question.
Is the direction of the copper 2 moments chosen? Is it spontaneously chosen?
No, it's chosen by the direction of the magnetic field due to the dipole fields. From the dipole fields due to the 4 copper 1 spins that surround them.
But they haven't ordered yet, right? At high temperature.
Sorry.
So this is below the ordering temperature of the.
This drawing is below TN1,
Okay. But
above TN2, where TN2 is the temperature where the copper 2s themselves order. So think of the copper 2s again as it's just a paramagnet with a field applied to it.
Yeah. Okay. Also, how do you get information that it's Nile order? That if you go one lattice step to the right, that you flip spin from your measurement?
I'm sorry, one more time.
How do you get the information that if you go one lattice side to the right, that you have flipped spin from the measurement, like the lattice translation information?
How do we get lattice? So the nail order is being picked up through this copper 2 site, right? Because the copper 2 site is uniformly pointing in this direction. So that's what picks out. That's what picks out the direction of this big lobe. So if you go to, as I'll show you in a second, if you go to a different domain where that direction of M is changed, you'll see the orientation of that lobe also change.
Oh.
Okay.
Thank you. M, that is a report of L.
Yes, exactly. M reports on L. I hope that answered your question. If it didn't, please come back to it after I show the next few slides. Okay, so I think I finished on this slide. Okay, so challenge 1, I think sensitivity, we managed to satisfy. The next question is spatial resolution. So typically magnetic domain, antiferromagnetic domain walls are very small. are very thin. You know, how do we overcome that? It turns out that you know, well, I'll show you in a second. The domain walls are pretty thick in this material, which makes them much more easily resolvable. But before I do that, let me tell you a little bit of a story about you know, the magnetic domains found in this system. Okay, so this is just a regular, you know, microscope image of a single crystal that we use. And if you take an SHG image of this, so think of this as taken using is an image taken in the second harmonic channel with your polarization fixed along a particular direction. Let's say along, you know, the direction of one of the big lobes. Okay, and so you'll see this sort of black-white contrast. Okay, that's obviously invisible in the microscope image. And if you go in and you do these polarimetry experiments on each of these domains are very big. It's 100 microns. So you can shrink your beam down, you know, to whatever, 10 microns and do a little polarimetry experiment on domain A, domain B, and you'll see that the lobes are sort of rotated by 90 degrees, telling you sort of locally what the orientation of L is. Okay. Okay. So the interesting thing about this compound is that if you were to take any collection of samples you want and continue to cool them down, you'll always only find these two domains. You'll always only find up. You'll find 2 out of 4 typically. Okay, and the reason is because it took us about a year to figure this out. But the reason is because the Earth's field is enough to train the direction. Okay. Yeah. So Kyle was very painstaking about this experiment, but doing the experiment in different locations of our optical table turned out to affect the results. But in any case, we now know the reason why there are only 2, because the direction of the Earth's field sort of biases, you know, left over right, up over down. Okay, and you can also ask, whether this compound is completely fourfold symmetric, rotational symmetric. Turns out it's not really, meaning that there's a very, very, very small easy axis in each of the domains. So you can think of it as having a very weak orthorhombicity that sort of favors, you know, this patch being, you know, horizontally oriented, this patch being vertically oriented. Okay.
So can you make a small compass with this? I mean,
you could.
There's probably better ways to do this.
There are better ways to do this. But and these samples are quite, you know, they're quite. I think they're not the easiest things to grow either.
David?
It's also sort of modulo 90 degrees. So.
David, would you be able to have a magnetic field in your lab that would cancel the Earth's magnetic field and see all 4 domains?
Yeah, so we've done that experiment. You can sort of try to shim it off, and some will spontaneously appear. But there's another way to create those, and I'll show you how to do that with light, actually. Okay. So if you don't want to do the experiment where you're sort of very carefully canceling fields or putting this in like a mu metal shield or something, you can actually create different, you can create the different domains with light. Okay, and so this is how you do it. So this is a recipe again, Kyle figured out. Up here is the schematic of what you're seeing downstairs in the SHG image. Okay, so here you've got, again, 2 magnetic domains. And if what you do is you apply a small in-plane magnetic field. In this case, let's say you orient it to the right. But you apply a field that's a little bit less than the coercive field. So just not quite enough to completely sort of flip that domain from pointing left to pointing right. Okay? But then you come in with a laser beam and you shine it, let's say, on this patch. That locally heats it up, which then lowers the coercive field. So that region now gets flipped. Whereas
one question. If you apply the field H to the right,
yeah,
or whatever,
yeah,
don't the 2 magnetizations, are they still of the same size?
Oh, the magnitude of the magnetization?
Yeah.
We're applying a very small field, you know, on the order of, you know, an Oersted or something. You're right. If you apply a large enough field, you can, you know, polarize them even more. But on the scale that we're applying, it's too small to have a noticeable effect. Is that okay? Okay, so the first thing I want you to know is that's the trick that Kyle came up with to sort of kind of deterministically put in a 180-degree domain wall, which are very hard to find naturally. You can do this it turns out you can do this at different positions. So if you shone the magnetic field somewhere else, you would create the domain wall there instead of here. Okay? So this is the same piece of crystal, just on a different, after a thermal cycle. Okay, and so, nominally what we think is going on is that across one of these domain walls, these are antiphase or 180-degree domain walls, and so the L's and the M's are rotating by 180 degrees. And I'll show you experimentally that that's the case in the next slide. Okay, so if you start looking at the image on the left, okay, so this is, again, an SHG image across one of these optically created antiphase domain walls taken in a particular polarization geometry. Yeah, Hannah?
Might be a silly question, but if you go to the previous slide, how do you know it's a 180 domain wall and not that it doesn't flip up and then flip back down in the same direction?
Just by locally, again, doing the polarimetry experiment.
Okay.
And you'll find that the lobe here is pointing this way, the lobe here is pointing that way. Yeah. So we always have to recheck with the polarimetry.
Okay.
Okay. Any other questions? Yeah, Ilya?
Just to make sure I understand, so this field is the field of these cuprates that are like in the diamagnetic.
In
the probe cuprates, not the ones that are in the antiferromagnetic order. The not ordered cuprates. Copper atoms.
So you're asking.
So these arrows are the magnetization of this additional copper.
This arrow is the magnetization of the copper 2 sublabs. So can I add? I need to add one more degree of detail, which is that the copper 2s are magnetized because of the dipolar field of the copper 1s, but there's a back action of the copper 2s on copper 1s leading to a small canting. So in reality, both contribute a little bit to the M.
Mm-hmm. Okay. So, but the Earth's magnetic field affects these coppers, and then those coppers affect the antiferromagnetic order somehow?
The Earth's magnetic field affects all of them. It's hard for me to address the chicken and egg question. Is it?
But the antiferromagnetic order doesn't have magnetization, so...
There's a small canting, which I swept under the rug. Yeah. Yeah, thanks. Yeah, Angel?
David, so just a question about how you've labeled your image here. So I imagine that bright is in one particular, on one lobe, is that right?
The bright should be sitting on one of the big lobes.
One of the big lobes. So why did shouldn't pointing one way be bright and pointing the other way be dark?
Let me think. I could be wrong. Let me think. No, you're probably I probably misspoke. It's probably sitting normal to the big lobe. Sorry. Yeah. So I think these were taken with these were taken along this with polarization here, so that two different orientations of the big lobe look the same, and then the 90-degree lobe is the small one, is the darker one. John? It's 5 minutes. Oh man. Okay. John, it's okay. No, don't be discouraged from asking. Okay, I'm going to zip through some. I wanted to say a few things about sort of like proving we did this and that. Let me skip those and so I can accelerate to the punchline. Okay. Okay. So you'll have to believe that these are 180-degree domains. You can do line cuts through them. It turns out these domains are really wide. They're about in this particular case 9 microns. Just to give you a contrast, typically if you look at more common AFMs, you're used to numbers like in the tens of nanometers. So this is huge, and the reason is because it's kind of special to cuprates. They have extremely large exchange, and they have very, very small anisotropy. Okay, it's very close to being an isotropic magnet. The ratio of those numbers determines the domain wall thickness, and so in this case, they're really, really wide. So that makes it easy to resolve, okay? And moreover, because they're so wide, you can actually take polarimetry plots as a function of space. So you can cut through and do polarimetry plots even within the domain wall, and that's how we determine that the domain wall is actually rotating. You know, it's a Néel wall. It's sort of got this, it's rotating in the plane from 0 to 180 degrees continuously. Okay, so I can answer questions about that later, but in the spirit of saving time, let me gloss over the proof and just sort of take it on faith that we can resolve how the magnetization is winding as you go from one side of the domain wall to the other. Okay, a big challenge in this field is reversibility. So, you know, typically, a common way you measure a domain wall velocity, let's say that's driven by a current pulse, is by taking a static image before you apply the current pulse, applying the current pulse, and then taking a static image afterwards, measuring the distance the domain wall traveled, dividing that by the time duration of the current pulse to get a speed, okay? And generally, you know, videography of domain walls is very difficult because these are not typically non-reversible. You push it and it just stays in the newly pushed position. Whereas for, you know, these sort of pump probe measurements, you have to do many, many pump probe cycles to get statistics. So how do you do real-time imaging if it's non-reversible? And you can't do single shot. Okay, so the first thing you do, the recipe we did was the following. So first of all, these materials are you know, good quality, but there are a lot of defects. You know, chemical impurities, maybe structural imperfections at various locations in the sample that can lead to some stickiness of the domain wall. And so the first thing we do is we have to find a patch of sample that's relatively clean, meaning that, and how do we define clean? Well, we apply a progressively larger magnetic field, watch the motion of the domain wall, and then reduce the magnetic field in the opposite direction and make sure that, you know, as the magnetic domain wall is moving back and forth, it's not encountering some defect that's pinning it.
But when you say move, you mean this thing stops or it just keeps on moving, and how do you sample it?
Yeah, so in the case of a magnetic field, it's just apply constant field, image, static image. Turn up the field a little bit, image again.
Right.
And
it will get stuck with it. No.
So oftentimes, so let me just show the movie and then I'll answer your question. So this is magnetic field going up in this direction, and then it's going back down again, back to 0, and then to the opposite direction. And you can see that
There will be a new equilibrium position every time I change the light field.
every time you change it,
Those is an equilibrium position.
yes, yes. But the important thing in this experiment is that as you go back and forth, you don't see it's never getting stuck. Oftentimes, if you go in a bad location, you'll see that actually it gets pinned. So there's a range of fields where it's not moving and then suddenly it moves again. So we first have to pick a region where it's clean, the movement is unhindered. And then the second thing is, you'll notice if I now apply a laser beam, and then I drag that laser beam around, those are denoted by the red lines, the domain wall actually follows the position of my laser. Okay, and we can talk about details later, but the empirical fact is that there's a way of using heat gradients to localize the domain wall. And so that's our restoring force. If we shine lasers at a certain location, even if we pull the domain wall away and we release it, it's going to go back. So that's how we get the reversibility. Okay, so with this trick, we're now going to be able to do pump probe measurements.
How does the domain wall know that you're on the right or on the left? I mean, you're pushing it this way, you're pulling it the other way.
So in this experiment, it's just a field. Oh, here.
Look, if you look at the lowest picture,
Yeah.
You shine the laser pulse to the left of the domain, but it seems that the laser is dragging it. Whereas when you shine it to the right, it seems that the laser is pushing.
So this is, it's a matter of scale. So these beams are actually very large. These are, the beam size is probably as big as the bar, actually. This is sort of just the center of the Gaussian. Okay.
So it's always to the right.
It's always, yeah.
No, I mean,
It's
always to the right. Or no?
the peak is where the red thing is, but it seems like it just always wants to be near the maximal intensity, the hottest spot. Okay, so now this all is work up towards the last piece, which is, okay, now having the spatial temporal resolution. Okay, so we're going to do an experiment where we're going to pump it with 1.5 eV light with the duration of about 100 femtoseconds, and then do this reversible sort of time-resolved imaging. Okay, okay, so here's a MINIC domain, 180-degree domain wall on one of these clean regions. I'm plotting L down here just to show you the sense of winding. And this is an experiment. And the pump light, we chose to be a bit elliptical, okay, for reasons I'll talk about maybe later. But anyways, this is the shape of a pump pulse. So part of it is overlapping the domain wall. We do this experiment with different polarizations: linear, right circular, left circular. And let me just play a video of what happens with the linear first. Okay, so this is now videography of a domain wall after being pumped. Okay, so linear polarization. Okay, you might have missed that, but I can play it again. Okay. Okay. So the geometry of the wall doesn't change, but the intensity of that wall, you might have seen a little darkening and rebrightening. That's just from the presence of photodopants partially suppressing magnetization. Okay? Now let's move to the circular polarization. So if you go to left circular, the geometry now changes. The domain wall got plucked out to your right. And if you go to your left panel, right circular polarization, the domain wall gets plucked to the other side. Okay, and so the helicity of your drive somehow determines the directionality of the force on the domain wall. That's lesson number one. Okay, I can quickly go through this. This is just, fits to those images and evolving those in time to look at the disturbance of the wall. And the takeaway point really is that the wall not only gets pushed out left or right, but also gets, but the disturbance actually extends in the y direction over a spatial region bigger than the beam spot. Okay, so these effects are really not just local to where the beam is hitting it. And it's maximized, the force, if you like, is maximized at the pure circular polarization, polarizations. Okay, so the next item I want to talk about is the effect of domain wall winding. So, in fact, there are a couple different types of domain wall that you can realize, and we, again, through a bunch of iterations of the experiment, managed to sort of realize all four types.
Finish this and then.
Okay. Okay. Sorry, John. All right. There are four types. Starting from left to right. There's counterclockwise winding, so think of this as sort of a winding number, maybe going this way, right? You can time reverse everything. You can time reverse that. It's the same winding, but the orientation of the spins are reversed. Or there's clockwise winding, and again, there's time reverse pairs. So there's four types of domain wall you can realize, okay? And I'm going to tell you a little bit about how each type of domain wall reacts to circular drives. So the first thing I wanted to show you is what happens if you find two domain walls with the same winding but are time reversed partners of one another. And what happens if I drive them with the same helicity of light? Okay, and so let's look one at a time. Okay, so it gets pushed to the left, and then this one also gets pushed in the same direction. Okay, so it seems like for the same helicity of light, time reverse partners get pushed in the same direction. How about for domain walls with opposite winding? Okay, again, I'll play the two videos. With the same helicity of drive, now the walls get pushed in opposite directions. So it seems like it's the combination of the winding of the domain wall and the helicity of light that determines the direction of the force. Okay, so again, together with Ran Cheng and Hentao Zhang at UC Riverside, we sort of came up with both a toy model and numerical simulations that seem to be consistent with this picture. Basically, here's a schematic of a domain wall. And if you think about sort of a global rotation near the domain wall of all the spins, that effectively imparts a domain wall motion. In this case, going to the right. And for the time reversed partner, the same sense of rotation also pushes the domain wall to the right. Okay? Going through the same exercise, but now for domain walls of opposite winding, results in domain wall motions that are opposite to one another. Okay? So this picture, this global rotation, is consistent with our observations. Microscopically, I think I have like 2 slides left. Microscopically, what we think is happening is that your circular pump is exciting, an antiferromagnetic resonance mode. Okay, the sort of precessions of the 2 copper-1 sublattices. And forgive me for being a little bit fast here, but basically we have ways of directly resolving this AFM resonance mode. It's a very low energy mode. And the time scale with which this mode is processing matches the time scale over which the domain wall is moving out. Okay, so anyways, you can quantify all this. You can plot positions versus time and then derive velocities from that. And we can, with a fluence of about 8 millijoule per centimeter square, we're achieving domain wall velocities of about 50 kilometers per second, which is very fast. The speed of sound in Cooper rates is about an order of magnitude smaller, and this is really kind of approaching, magnon velocities, a little bit shy of Fermi velocities. And as a comparison, to several other magnon-driven domain wall mechanisms, including thermal magnons, coherent magnon-induced spin transfer torque, our mechanism actually gives you very, very fast domain wall motion. Okay, thank you to these people, and especially shout out to Kyle, who's the one sort of leading all of this effort.
We have time for a couple of questions. John, please take it away.
Thanks. This is super cool. So for the linear polarized light, you said it basically had just left a little blip because of some transient photo doping. But presumably the circularly polarized light is at the same frequency, so is it not also photo doping? And is that the origin of this coupling, or?
So in all polarizations, you'll see that little blip.
Right.
The difference is in the circular case, it imposes sort of a fictitious magnetic field, if you will, that launches these magnon modes, whereas you can't do that with the linear.
Should I think that it's photo doping with like chiral carriers, or?
We don't know, frankly. We don't have a microscopic model, but that could be one thing, right?
Thanks.
That could be one possibility.
Yeah, when you stressed that this is different from the speed of sound, did you have some expectation, like that the 2 should be linked because of some magnetoelastic coupling, or this is
No. The short answer is that we didn't go into any expectation, and I don't think there's no reason why they should be. One is this one should be bound by sort of the magnon group velocity.
I have a quick question. The fact that this guy is moving supersonically should also give rise to some sort of Cherenkov sound wave coming off. I mean, did you ever?
We've thought about that, but we haven't gone to the requisite speeds. Okay, so we haven't gone to the necessary speeds where it's exceeding the magnon velocity.
The sound velocity, if the magnon.
Oh no, I think
It would launch a sound wave on a sort of, it would be mapped to, say, it would generate a Cherenkov sound wave.
that's if it's dragging along some lattice.
If there is some magnetoelastic.
Right. Yeah. So that we haven't seen.
Right. That was Of course, it may be completely response. So
But
very good. I think we are fashionably on time, and we should thank David again.